The Fermi Paradox. 2 trillion galaxies in a universe, trillions of stars in each, yet we're alone. Statistically, we should see evidence of intelligent life everywhere, yet the universe looks empty of life besides us. Why? This equation might explain it actually. According to this, if someone molded a region smaller than an atom to just be slightly denser than its surroundings, it will later form superclusters spanning billions of light years. And that opens the premise. What if we might be living in a cosmos that's already been shaped by some beings from the far past, and we just don't know it? To manipulate the entire universe, any civilization in the past would see the universe as a film. Act 1. The Inflation Prologue. Spacetime snaps from being smaller than a proton to the size of our galaxy in less than a trillionth of a trillionth of a trillionth of a second. Act 2 is Radiation Domination, a chaotic blinding soup of light. And Act 3 is the era of matter, where the first stars ignite and the universe cools. Stop. Every era of this timeline is noise, except one brief window. A cosmic dawn just a few million years after inflation. A time when the universe was still soft clay, waiting for a hand to mold it. Miss this window and the modern structures have already hardened. The cosmos becomes impossible to change. But during that window, a civilization has 3 ways to change the structure of our universe. Imagine if you were the one with that power. Ask yourself, how can the same action be 100 times more effective just because of when you did it? At the center of this strategy is a rule as simple but incredibly powerful. The simple equation is delta as a function of time is proportional to A of t. Now, what does this mean? This says that tiny overdensities, delta t, regions where matter is clustered more than average, grows proportionally with the expansion of the universe, A of t, which means early advantages compound exponentially. We set the present universe as having a scale factor A set to 1 for simplicity. A of 13.8 billion years is equal to 1, meaning 0.5A is half the size of today's universe, and 2A is doubling that size. Here's what that looks like with actual numbers. Say the universe has an average of 100 atoms per cubic meter. You create a region with 101 atoms. That's 1% denser. That's your delta equals 0.01. As space expands, gravity amplifies this tiny overdensity since stuff is more gravitated towards this region, causing it to grow roughly in proportion to the scale factor A of t. Now, here's where it gets strange. If you create that 1% advantage when the universe was 1,000 times smaller than today, that delta equals 0.01 transforms to delta equals 10, a 1,000 times multiplier. But if you create that same 1% advantage when the universe was only 10 times smaller, it grows just to delta equals 0.1. Same effort, same physics. The only difference is 100 times less impact. But these numbers are only a part of the story. Here's what makes it truly powerful. It's not just that early changes grow larger. The medium itself was different. Remember Act 2 of the film? In the beginning, space was so packed with matter and radiation that you might as well compare it to the density of steel. Except that the medium itself was a fluid because atoms didn't exist back then, so no chemical bonds existed due to the extreme temperatures. This caused matter and radiation to move together as a single fluid, capable of transmitting sound waves faster than half the speed of light, called the photon baryon plasma. Heat one region and the pressure wave whizzes through space, affecting regions hundreds of thousands of light years away. In today's universe, any energy released in a galaxy mostly dies there. It's trapped in a local pocket, like a supernova. Which raises an obvious question. So, if you can act during the cosmic dawn, what would you actually engineer? 10 billion years from now, your descendants will face whatever the outcome of the cosmic dice randomly delivers. Maybe harsh conditions, places where giant stars live fast and die young, disrupting planet formation, zones void of heavy elements essential for complex chemistry, or whatever else life needs. Then again, maybe favorable circumstances, steady, long-lasting stars, stable orbits, rich, heavy element abundance. By creating overdensities, you discover that you can bias the odds. Not control outcomes, the universe is too chaotic for that. But you can tilt probabilities. Make favorable regions more likely. Suppress hostile environments. The question becomes, what does the far future need most? Your scientists present 3 methods. Each manipulates overdensities differently. Each bets on a different answer to what matters most for life that doesn't exist yet. The first physicist, Kip, says we should suppress chaos. The smallest overdensities, regions with delta barely above 0.01, will form dwarf galaxies. Small, dim, magnetically active stars prone to flares. Unstable radiation environments, short metal enrichment timescales. But there's a threshold. We can restrict the creation of stars thanks to their gene's mass, which tells us if a cloud of gas will collapse into a star or expand into nothingness. However, around 10,000 solar masses is where thermal pressure balances gravity. Below that, halos can't cool and collapse. They just expand. But here's the trick. That gene's mass threshold isn't fixed. It depends on temperature. And in the early universe, you could change the temperature of entire regions with relatively little energy. Flood a region of energy raises the gas temperature, which raises the gene's mass from 10,000 solar masses to 1 million solar masses. Suddenly, any clump smaller than 1 million solar masses can't collapse anymore. Billions of years later, your region is dominated by large, stable galaxies, with long-lived stars and steady metallicity growth. Fewer systems overall, but each one far more hospitable. The risk, however, is that if you heat too much, you don't just suppress small galaxies, you suppress all structure formation. You create a cosmic void. Oops. But wait, Dr. Zorpglarp said, we should create predictability. You see, natural structure formation is scattered. Overdensities appear where quantum fluctuations happen to be during the Big Bang, producing isolated galaxies and random clusters. The result is random galaxies and clusters of galaxies. So if you wanted to shape the universe to create neighborhoods of predictable, stable stars, what kind of tool would you possibly use? Something enormous, dense, and gravitationally dominant. Something capable of bending matter over hundreds of millions of light years. Perhaps a supermassive black hole. 1 million solar masses, and that black hole itself is an incredibly extreme overdensity. Matter strongly flows towards it over time. Instead of scattered formation, you get organized clustering. Place a supermassive black hole now, and as it feeds, it blasts jets and winds that clear space and push surrounding gases into shells. By the time that galaxies form billions of years later, they're all organized around a central anchor, making a galaxy. That is in fact why most big galaxies nowadays host a supermassive black hole in the center, like the Milky Way. The risk? If the black hole grows wrong, too fast or too slow, all formation would be suppressed. But our last astrophysicist, Bob, leans forward and says, we should maximize resources. The thing is, everyday matter like from the periodic table, isotopes, subatomic particles are in a category called the baryonic matter. However, this type of matter only makes up 15% of the total mass in the universe. When manipulating over densities, we are missing the other 85% of the cake. And that goes to dark matter. We did a deep dive of it in this video, but essentially it's the invisible matter that is extremely important in making galaxies. If dark matter density is higher in one region, overdensities grow faster and deeper. A region with delta equals 0.01 in normal matter, but added with 10% more dark matter, effectively has delta equals 0.011. That compounds over billions of years into significantly larger structures. This tool is much more powerful than messing with black holes or gas temperatures. This dictates the very sizes of galaxies. More structure formation means more stars, more supernovae, more heavy elements scattered into space. Future planetary systems inherit richer chemistry, more carbon, oxygen, nitrogen, and iron. They're building blocks of complexity. The catch is that with our current understanding of physics, we have no idea how to manipulate dark matter. No mechanism to even speculate about. This method only exists in math. So, your civilization debates. Some argue for stability, long-lived environments matter more than abundance. Others argue for organization. Predictable neighborhoods reduce existential risks. Still, others argue for enrichment. Complex life needs rich chemistry above all. There's no right answer. Each method optimizes for different assumptions about what future life requires, and you can't test any of them. You choose. We are, by all accounts, incredibly late players. We've arrived when the bricks were already laid. If the cosmic dawn manipulation is real, if someone actually committed to it 13 billion years ago, then the conditions we observe, our stable orbits, our favorable metallicity, our quiet galactic neighborhood, might not be random chance. They might be someone's choice. Someone who looked at the soft clay and decided to shape it. Not for themselves, but for whoever came after. And if that's true, we're inheriting intention. Someone believed the far future was worth their present. That strangers mattered enough to spend a civilization's energy shaping probabilities they'll never see resolve. We can't prove it, but we can ask. When we look at our fortunate circumstances, are we seeing luck? Or are we seeing a gift we never knew we received? Maybe the Fermi Paradox isn't about absence, it's about inheritance. After 13 billion years, an engineered region looks exactly like natural variance. You can't prove a galaxy cluster was biased versus formed randomly. Success is invisible. But if we're living in an engineered domain, that changes everything. It means someone 13 billion years ago looked at the cosmic dawn and chose to garden it for strangers in an unimaginable future. Because they believed life mattered more than recognition. That's the most profound act of generosity in cosmic history. They spent their civilization's energy knowing they'd never see if it worked. And if it did work, if we're the proof, then the universe isn't empty. The Fermi silence isn't loneliness, it's gardeners who finished their work billions of years before we existed to say thank you. Which means we inherited a choice. If humanity ever reaches that capability, do we plant seeds for the far future? Not for reward, but because we learned some acts echo across billions of years. The cosmic dawn taught us the most powerful force isn't energy or gravity. It's choosing to build a garden for strangers, knowing you'll never see it bloom. When you look at the stars, you might be seeing the greatest act of faith ever committed. The question isn't where everyone is, it's whether we're ready to become the gardeners too.